The first day of the fourth edition of the Quantum Industry Summit of OPTICA is in the books now, and it was a great event. The whole idea was to get all the quantum companies on QKD, on quantum computing, on quantum communication, to see how they can work together. And let's see the result. Today, we are entering the Concord because we couldn't imagine a better place to have the reception of the Quantum Industry Summit. I'm here in the Concord, and as we enter the Concord, we're gonna meet some of the attendees of the OPTICA Quantum Industry Summit this year and learn what is the key takeaways that they found from the first day. Piotr, you are on the first day of the Quantum Industry Summit. Simon, how do you think the first day went?
Oh, I think it's a really good event. I just think the depth and breadth of the community is a really amazing thing that came out of it.
And Simon, what do you think of being here in the Concord today?
Oh, it's fantastic. I used to fly over where I work, and so we used to see it from underneath. So it's great to go.
Simon, be very careful. We don't want you to hit your head, and let's get out a bit and meet some of the other attendees. Mark, we are on the first day of the Quantum Industry Summit of OPTICA. You are here next to the Concord. How do you think the first day went?
Oh, super well. It was very interesting. The one thing that I find interesting is we have all these companies that are competitors, and I found it very interesting to see how open everybody was about collaborations. We're all following the same objective, and goal ultimately is to convince a customer and win the market as much as possible, as soon as possible.
Mark Niklas from EduQuantic, today you were very clear. You want to collaborate with everyone and you offer the platform for collaboration. Could you tell us a bit more about that?
Yes, so I've never seen any telco operators that's going to say we accept to be locked in with one vendor. Multi-vendor policy is everywhere. So the only way to be stronger together is to make sure that we have interoperability between systems. And we're offering to QKD companies to test their equipment with our software so that they can then prove to end users that they have the opportunity to be compatible with our software or anybody else.
Let's go for dinner.
New dates and location have been announced for the 5th edition of the OPTICA Quantum Industry Summit in 2026. We're moving to the summer, June 16th and 17th at the famous Scottish Events campus in Glasgow, UK. The formula of top-level keynotes and extended power networking breaks, plus receptions, remains the same. Registration opens soon. And remember, exhibition booths and sponsorship packages like this year include summit tickets and wide brand exposure during the sessions. Active OPTICA corporate members get a 15% discount. For more details, check out the website or send a message to Carmen. See you in Glasgow as the meaningful conversations continue.
On Tuesday, 18th November, the OPTICA Online Industry Meeting is again on quantum computing. This year has been the year of IonQ. We have seen not only the acquisitions, but the huge developments on developing the first ion-based quantum computer. We want to ask Jeremy Sage, Senior Director of Technology at IonQ, how can the photonic industry contribute to development of the next generation ion-based quantum computers? He will join a panel of senior experts in quantum computing with a shopping list from the photonic industry. This online industry meeting is very timely because it will be the week after the OPTICA Quantum Industry Summit at Bristol. So then we will also review the learning. This meeting is free for everyone, and that's thanks to the sponsorship given by Ligentech, Fix, Polariton Technologies, transient, and nanoscribe. Okay, let's start the discussion.
Okay, welcome everybody to today's OPTICA Online Industry Meeting on quantum computing. I'm John Pugh, Technical Director for PIC and Quantum Technologies at OPTICA. And it's great to have you with us, especially just 1 week after that Quantum Industry Summit in Bristol. So quantum computing is now entering a new phase. We're seeing more IPOs, companies testing the public markets, more mergers and acquisitions, and more investment than ever before. So the message is clear. This technology is moving from promise to real commercial momentum. But every platform, ions, atoms, photonics, superconducting, is now hitting the same fundamental bottleneck, photonics. Integrated optics, packaging, coupling, sources, detectors, and system stability will define how far and how fast quantum computers scale. The good news is the collaboration across the ecosystem has never been stronger. Hardware companies, foundries, packaging houses, startups, and end users are co-designing solutions in a way that we've never seen before. And today represents that full spectrum, from system builders to enabling technologies, all here to share what the photonics industry must deliver next. So, let's remind everyone what we're here for today. So with the support of the meeting sponsors, Ligentech, Fix, Photonics Assembly, Polariton Technologies, Quantient, and Nanoscribe, we've brought together integrators, those companies who put together utility-scale fault-tolerant quantum computers, IonQ, Continuum, and Orca Computing. They're all here to share their shopping list and what we can do for them. But also, we have the technology enablers who want to make it all possible. The extensible quantum network architecture of MEMQ, quantum dot-based single and entangled photon sources, also microwave optical transducers from Icarus Quantum, development of next-generation advanced processing technologies, materials and integrated photonics platforms from IMEC, leading expertise in photonic packaging from Fix, low-loss silicon nitride and heterogeneous integration of electro-optic materials from Ligentech, femtosecond laser writing of micro-optical, photonic, and micromechanical structures directly into glass from Femtoprint, and one of the leading providers of engineering simulation software that makes all the design of these systems possible, ANSYS. The idea here is to match their technologies, not only with the integrators, but also everyone in the room. You're all panelists. You're all here to, when invited, unmute and ask questions and share what you can do for others and what others can do for you. Remember, we do this because we're on a mission to work for and help our OPTICA corporate members. So if you're not a member yet and would like to know more, then please get in touch with me, Helena, or Olga, my technical director colleagues, and we're always happy to meet and share all the benefits with you. I also want to remind you we have a great program of online industry meetings, and today is our final OIM of the calendar year, where we're more or less closing the International Year of Quantum events at OPTICA, before we return in January to discuss lighting and heterogeneous integration in silicon photonics. We also love to meet our members face-to-face. We've just had one of our flagship events, the OPTICA Quantum Industry Summit you saw at the start in Bristol, which next year moves forward in the calendar to June to co-locate with OPTICA Quantum 2.0 in Glasgow around a shared exhibit, creating one of the largest gatherings in quantum across the calendar. On the 19th of January, we have our iconic VIP reception at the San Francisco Museum of Modern Art. We're also live in YouTube, thanks to the support of our sponsors. So welcome to the YouTubers of the world. I have you on a separate screen. It's great to have you here. So over the next 90 minutes, if you have questions, write them in the chat and I will voice them in the Zoom room. I'd like to thank in advance all our speakers for joining this meeting today and being prepared to answer all of your questions. So please keep them coming. If you type them in the chat, we will welcome you to unmute and join the conversation. So let's have a fantastic 90 minutes. And to begin today's meeting, we're showcasing a great collaboration between IonQ and IMEC. And joining us are Jeremy Sage, Senior Director of Technology at IonQ, and Amin Abbasi, Senior Business Development Manager at IMEC. Together, they'll share how IonQ's leading ion trap quantum computing architecture is now being paired with IMEC's photonic integrated circuit and trap fabrication expertise. This is a pivotal moment in the quantum photonic supply chain, and you're about to hear why. So without further delay, Jeremy and Amin, the floor and the attention of everyone is yours. Welcome.
Thanks so much, John. It's great to be here. I'm hoping everyone can hear me well. Thank you to OPTICA for the invitation to speak to you today on behalf of IonQ, along with Amin Abbasi, as you heard, on behalf of our friends at IMEC. As John said, I'm Senior Director of Technology at IonQ. I have about 25 years of experience in the field of quantum computing, quantum information processing, including sensing and networking. And at the heart of what I've worked on over a long period of time is photonics, which lies at the center of the control technology that we need for these systems, as I'll try to illuminate to you as we go on. First, a little bit about IonQ. Let me see if I can advance my slides here. Okay. So, over the past few years, IonQ has been building something which I think is truly unique. What started as solely a quantum computing company is now the only quantum platform company in the world. It covers not just computing now, but quantum security, quantum sensing, quantum networking, and all the way to computing, of course. We see these areas as highly synergistic and helping to drive technology and product development and product really across the entire space. So, starting with quantum security, this is, post-quantum cryptography and QKD solutions, through quantum sensing technologies, leveraging these really precise measurement capabilities for ultra-high precision and accurate sensing, through to defining and developing the global quantum internet that is connecting sensors and quantum computers and single photons and quantum information across a large area of space and land, and then finally through to quantum computing, which is really I think the big gorilla of the application space for quantum technologies. This is where the raw processing power, we believe, can solve problems that humanity is facing exponentially faster with lower power than we would ever have thought possible with classical computers. And so, we really see these things as working together, driving one another in a synergistic fashion, as I said, and it's something that we plan to leverage going forward. IonQ was founded in 2015 in College Park, Maryland, in the U.S. Of course, it's a spin out from academic quantum research labs of Chris Monroe and Jungsang Kim. And while we highly value and cultivate strong R&D mindset, in just 10 years, we've gone from these humble beginnings, I would say, to a truly global company spanning over 10 locations in 5 countries, with our number of employees now exceeding over 1,000 people. So I think this is really one of the indicators of how impactful and exciting the quantum space is, and I've been an honor and a privilege to be part of this and witness this expansive growth over my own personal career. At the heart of IonQ's architecture, are trapped ions and even neutral atoms for our clocks, and even solid state quantum memories and things like that. But really where we focus is on, our kind of natural qubits, things that are fundamentally identical, qubits that we, ultimately don't have to manufacture. And what we really want to take advantage of is their, natural identical nature, their long coherence times, the ability to perform, universal gates and highly scalable control with very, very high fidelity. Such that, the primary challenge in front of us is one of not physics, but of engineering, where it's the control technology that is the most critical scaling lever that we need to develop in order to realize some of the greatest applications that we have in front of us. As John mentioned earlier, really it's photonics that lie at the heart of this. It's the primary means by which we interface and particularly send information in and get information out of these quantum systems. As we think about scaling these systems up to control more of these quantum bits of information. We want to shrink these systems down and make them more manufacturable. It's bringing a lot of this photonics technology on chip is really a key that we see. So really we want to build systems that are photonically interconnected with one another to distribute them both as quantum memories and quantum networks and even modular quantum computers, as well as to achieve high connectivity and parallelization, ultimately driving very, very high fidelity operations leading to fault tolerance, and really bringing these component technologies together into full systems, full stacks. That is getting our software and our hardware working in harmonious synchronization to realize these applications. So what really are the needs that we have in front of us based on this control technology? So I think really at the heart of this thing, as I've already mentioned, is a lot of these scalable chip scale technologies. So we were looking for scalable ion trap technology for increased qubit and ion count, scalable generation, amplification, modulation, delivery, collection, and detection, visible to near IR light. I would maybe put an asterisk on the visible part of this spectrum. I think a lot of the technology in integrated photonics that has been matured over the past couple decades have been in the near infrared, and I think while we leverage those capabilities and that technology and even those wavelengths, a lot of where we're pushing is into the visible and into the near UV, and that's an area of real growth, I think, for the industry and what will enable us to grow as a company. And I think for many others in the quantum space as well. We're looking for scalable quantum networking hardware that includes low loss fiber, single photon detectors, optical wavelength conversion, optical switches, all kind of able to handle many channels. As I mentioned before, this technology, we really wanted to underpin this idea of modularity, both to enable replaceable parts, upgradable systems, to yield, improved system uptime, manufacturability, and of course, we wouldn't be in the quantum space if we didn't care a lot about peak performance, which the performance of these systems has to be exquisite. And then, in the end, as a company that's trying to deliver the best value to our customers, really driving down cost and system size is another key figure of merit for us. And of course, with all of these things, there are challenges, and with challenges come opportunities. And I would say, some of the challenges that we face, some of the headwinds really are really that quantum PIC volume demands are today, I would say, a poor fit for commercial foundries, right? We can't today throw designs over the fence. PDKs don't exist, and the volumes that we're interested in, while it's a high value per chip, the model of running tons and tons of wafers, just because we need tons and tons of chips, isn't really there. It's sort of a different model in quantum. And I would say this is particularly problematic for early stage development. Really what lies at the heart when you're doing this early stage development is you need fast iteration, right? And also you need clear off ramps to manufacturing, right? It can't just terminate as an R&D project. It needs to have a path towards being a reproducible, robust product in the end. And I think another main challenge is, for the quantum industry, it can really be cost and time prohibitive to be vertically integrated and to build and operate foundries internally yourself. And so in this light, IonQ has partnered with IMEC to really take advantage of IMEC's deep expertise in integrated photonics, as well as this R&D to production mindset. And this is something that we really looked for early in our photonics development. And so with that, I'd love to pass it off to my friend Amin Abbasi from IMEC. I'll let him introduce himself and then take it from there. And happy to take any questions later once we conclude. Take it away, Amin.
Thanks, Jeremy. Very happy to be here in another OPTICA event. And it is my pleasure to introduce IMEC. As Jeremy set the stage, there are challenges for integrated photonic for quantum, and I want to do some short introduction about IMEC for those that they are not working with us or they are not familiar with us. So most of the people, they know us as a R&D fab, but we are more than that. So this is the campus bird eye view of our campus in Leuven. Leuven on the far top, you can see the part of the city. It is a small city next to Brussels in Belgium. So last year it was a great year. Our 40th anniversary, we got 2.5 billion extra investment to expand our fab, and almost we are going to double our infrastructure capability by 2027. There will be new fab 4. It is indicated in blue here. It will be operational by 2027. It is new 300 millimeter fab. So next slide, I have also a bird eye view of the fab in Spain. So it is not built yet, but everything is approved, and hopefully by 28, 29, this fab will be operational. This is the good news and opportunity for the photonic community, I'm saying. So I cannot share more details on that, but it will be a great opportunity mainly for the photonic also industry. So this fab will be in Malaga. Hopefully soon will be operational. And the next slide. Yeah. So again, emphasizing about the IMEC DNA. So as Jeremy mentioned, there is normally for some application, especially on integrated photonic, the volume is not there to attract a big foundry like TSMC, Global Foundry, Intel, Samsung. So and you do the R&D work in the university or in small academic facilities, and you want to scale it with the using the CMOS tools, standard tools. So IMEC is bringing bridging the gap between these two extreme university academic and also the big foundries. So we are quite flexible to apply new materials, new method processes, new designs, DOEs, but using the standard tools, 200 millimeter, 300 millimeter, and do all the way process control, monitor, and the volume up to 1,000 wafer per year. And if volume goes beyond that, we will be happy to do the tech transfer to the foundry. Yeah. So what does it mean, quantum for IMEC? Similarly, we are also active on the both of all these three quantum computing, sensing, and communication aspect, but not as a making quantum devices, but we are the technology enabler. So we have a photonic technology, electronic, also 3D integration, that using standard, as I said, CMOS design and fabrication facilities to pushing the boundaries of quantum. For sensing, we are introducing new materials to co-integrate with our fab, diamond and silicon carbide. These are the new technologies that will be available at IMEC for the mainly sensing application, but it can be used also for quantum networking, for example. On quantum communication, also we have activities. There was a European project that this is one of the examples that we did the QKD between two Belgium cities doing using IMEC photonic technology. Just a couple of examples. And in quantum computing, it is complicated, right? There are different approaches, photonic-based, ion, atom, color center, spin, superconductor. So again, we are, as a technology provider, we have a luxury to work in all of these almost approaches. So for example, for photonic, we have a silicon nitride technology, aluminum oxide technology. For ion, dedicated also photonic structure, ASIC packaging. I mentioned the color center for the silicon carbide based and diamond based technology. We have a dedicated work on the spin based quantum, but this is more like a program mode, so partner can join together in the pre-competitive way. There will be same also approach for the color center, that as a technology hub, the wafer suppliers, tool suppliers, materials, they can go join all program and benefit from the shared IP model, but it can be also dedicated work, of course, for this one. And the last slide about the capabilities, and maybe I will also mention some needs. I know Optica always asks for that. So on the integrated photonic side, yeah, we have a silicon nitride, and this is the complementary of our silicon photonic that mainly we use it for telecom datacom application. But here we have a low loss silicon nitride. The thickness uniformity, it is important for the designer, co-integration with the active component like lasers, detectors, and 200 millimeter is available in production, 300 millimeters under development. We have advanced ASML litho capabilities, so if there is a need for the 300 millimeter, it can be even explored. On aluminum oxide, we got the new tools, 200 millimeter, and the recent results show amazingly a good result, state of the art, like less than half a dB at 360 near UV waveguide silicon aluminum oxide, and this can be co-integrated with the other modules that we have, like detectors and lasers. On the flat optics, also for steering and shaping the light, we have activities. We can do this work on the transparent substrate, the one example shown above on the quartz substrate. And also on the electronics, we have activity for the designing in the low temperature millikelvin regime CMOS component. It is quite generic for all other quantum application. And also new materials like niobium tinitride is also available as a thin film. Thank you very much for the opportunity. For the maybe one last, what we need from the partners, you know, we are silicon foundry, so we cannot do everything, right? 3.5, for example, is not available in our fab, so we normally do this 3.5 or lithium niobate as a hybrid integration. So we are looking for the partnership with the companies on 3.5 integration for the packaging, testing, reliability, design, simulation. So normally those are the one that we look for the partners. We have good partnership. There are a couple of them are here, like Fix IC here for the packaging. But yeah, always we will be happy to find a new partner. Thanks.
Great. Well, thank you so much, Jeremy and Amin, for kicking us off and showcasing such a great collaboration. So, Jeremy, we had a fantastic keynote presentation from Mihir Bhaskar, who's your, I guess, new senior vice president of R&D about a week ago. And he's also the former CEO and founder of LightSync. So the acquisition of LightSync gave you expertise, and also this collaboration with IMEC gives you more expertise in this area. So are you seeking to partner further on specific parts of the package, such as things like low loss fiber attach, for example?
Yes, absolutely. These are areas, I mean, I think as anyone in this business knows, you know, packaging is often the devil, right? That nobody likes to talk about, but it's a really big challenge. And absolutely, you know, I think you know, packaging is a big thing. Of course, you know, LightSync had developed, you know, a sort of a packaging technology as well that you know we're looking to leverage. But I think, you know, in the industry, you know, more widely, this is an area of great interest for us, especially, you know, as I kind of alluded to before, things that work at visible light. You know, some of the approaches to packaging people have taken, you know, they, you know, where there are epoxies, you know, in the path of the fiber, right, aren't as viable, you know, at these kind of very short wavelengths, you know, blues and things like that. So coming up with techniques that can handle, you know, I think the tighter alignment tolerances as well as some of these epoxy challenges are pretty key. So packaging is definitely an area of high interest for us. Looking for opportunities to collaborate there.
On that note, we have a question in the chat from Stefan Heinemann from Fix.
Yeah.
Stefan, would you like to unmute and ask your question?
Yeah, thanks for taking the question here, Jan. And I was interested what the top 5 challenges are in packaging, and you already mentioned the first few ones. But you know, obviously, low loss coupling seems to be very important.
Yep.
Are you also looking into low temperatures and the wavelength range?
Yes. Yeah. Great question. Yeah, absolutely. And that is another challenge. So, you know, many of these trapped ion systems, as I mentioned, we have a few technologies where things work at room temperature, and that's fine. That isn't as big a challenge. But for our quantum computing, while things don't primarily have to work at cryogenics, there are large advantages for working down at temperatures around 4 to 10 Kelvin or things like that. And there, we need to hold, fiber alignment packaging tolerances, at the sort of micron to submicron level, down from room temperature down to 4K. And so that is a challenge. And so we are looking for people that have that expertise that can help us out. We have some of that internally, but it is not a solved problem, I would say, completely.
Happy to work with you on that.
Great.
Located in the heart of cryogenics in Montana, so we know what cold means.
Okay, great. And of course, I'm quite familiar with you guys, and it'd be great to catch up. Absolutely.
Thanks.
Yeah.
Maybe something you can both provide some insight on is testing. Testing and the sort of cost behind testing is proven to be a bit of a bottleneck in commercializing any PIC-based system. So how do you envision testing, characterizing, and certifying these module level PICs before they're integrated into the full ion trap system?
Yeah, great question. I don't know if that's something that you want to take, or would you like
Yeah,
to
I can mention. So normally there are different type of testing, like wafers, optical testing, electronic testing also. So depending, the best is that you have a PCM structure and test structure on your wafer. So you cannot measure everything on your wafer. So it is best that to have some test structure on each die in the reticle, and you do these fast optical tests in line. Normally, those are also the wafer scale tools that are in the fab itself. And while you are adding layer on top of each other, you don't want to wait till end of the wafer come out. So in the middle, inside the clean room, still you want to do some like passive waveguide test measurement. So, and normally these are the highly demanding tools in the clean room, and there is a queue. So, but then afterward, also when you want to deliver the wafers, imagine that 20 wafers with the thousand of component on it. So normally we are also looking for the partnership via our customer or ourselves directly subcontracting those testing. So we have limited capability to do limited tests. But if it goes like in the production, normally this is handled by our customer or via subcontractor.
Right. And certainly a potential partner for you all is Microalign. Dario has asked a question in this chat. Dario, would you like to unmute and ask a question?
Yeah, found you mute. We are making fiber arrays with near perfect pitch, and I was wondering if anybody knows how to measure or what the pitch of a PIC is going to be when it's at cryo. This to be able to match the pitch of the fiber array to that when at cryo. It's another thing to measure.
Yeah. I think that these are small things, right? And so they don't move a lot, obviously, absolutely, right? As you cool them down. And so, we have not found that, I think, the actual like shrinkage of the PIC itself to be a dominant factor in the misalignment as you cool down and things like that. It's more just, a fiber array or fibers moving relative to the PIC, right? I think there's obviously some effect there. I think it's pretty small in the end. So I think in the end, tailoring a fiber array with a perfect pitch to a PIC, which is, I would say, as perfect as the fiber array, is a good path. And I think starting there is plenty. But I think having kind of this so-called perfect fiber array is an advantage, right? Because as we know, right, there's V groove arrays, but there's obviously offsets of the fiber cores and within the fiber itself, right? Which actually can lead to substantial errors. And so, kind of having fiber arrays where the cores are actually aligned on the perfect pitch is a big win, I think, in and of itself.
And
Okay.
just I'm sorry,
Thanks.
Darren, do you have a follow-up on that?
No, I said thanks.
Great. Finally, Jeremy, when do you expect to transition in your roadmap from prototype PICs to fully production scaled PIC-based ion trap modules?
Yes. So we are taking a very aggressive roadmap here at IonQ, and I would say we're in that process now. I mean, I would say it's today. We believe that we need these PICs that are going to be in our products, within the next year or so. So we're on that path now.
Well, thank you again,
technologies now.
both of you, for joining us. So yeah, looking forward to seeing the progress. So our next speaker is Zachary Vernon, Director of Photonics at Continuum. And Zachary recently joined Continuum after serving as CTO of hardware at Xanadu, where he led the development of cutting-edge photonic quantum processors. So at Continuum, he now drives the photonics and optical engineering innovations underpinning their world-leading trapped ion systems. And today I'll share what Continuum needs from the photonic industry next as they scale towards fault-tolerant architecture. Zachary, please take it away. The floor and the attention of everyone is yours.
Thanks very much, John, and appreciate the opportunity to be here. Good morning or good afternoon, everyone, depending on where you are. Yeah, so I'll speak about what we're working at Continuum, in particular around scaling our trapped ion quantum computers using integrated photonics, which is what I was hired for. As John mentioned, I'm relatively new to Continuum. I just joined in September. My background is in photonic quantum computing and hoping to apply a lot of what I've learned, taken out of the telecom band, and see if we can have an impact here in the visible and UV. Just a little bit about Continuum for those who aren't familiar with us. So we like to say, the largest integrated pure play quantum computing company in the world by a number of metrics. We have over 600 employees around the world, a few different sites in the US. I myself am actually based in New Mexico, in Albuquerque, which is where the newest expansion for Continuum is located. And this is a site that we're dedicating primarily and almost completely to photonic integrated component development as well as packaging. Of course, lots of work already incumbent over the past few years going on in our headquarters in Broomfield, Colorado, but New Mexico is going to be all about it, dedicated to photonic integration. Big news for us this year, actually just a couple of weeks ago, we announced the launch of our latest quantum computer, which is called Helios. This is a system really the most advanced in the world, 98 physical qubits, about 50 logical qubits, and that's really underpinned by the extremely high fidelities that have allowed us to now integrate and actually apply real error correction, something that is very exciting to see in this industry. Over 4 nines of single qubit fidelity, over 3 nines of 2 qubit fidelity, really punching well above our weight here in all the core metrics that are important. Now, I'm not going to talk much about Helios because it actually doesn't have too much integrated photonics in it. So really what I'm looking at is the roadmap beyond Helios, so Sol, Apollo, as well as some systems that are not, future generations that we're not able to publicly speak about yet. But as we're gradually going, year after year to these future generations of quantum computer, integrated photonics is going to play an increasingly important role in enabling that scaling. And so to that end, let me talk a little bit about what we're doing in integrated photonics in order to execute on that scaling. First, I'll start with just a snapshot of what the actual trapped ion architecture looks like currently in the Helios model. So this is a little bit different approach if you've looked at, familiar with some of the more traditional trapped ion approaches. We do not interconnect different ion traps in order to scale them photonically. We rely on direct qubit transports. We're physically moving ions around, and that happens by using this kind of lollipop-shaped structure currently, in which ions are loaded through the right side, and they kind of travel along this bus, and we can store them in this ring. So we constantly have them circulating, pull them out of this sort of storage or memory, and then have them actually implement gates in this quantum logic region. And this is all done electronically, of course. Now, how do we address these qubits? Well, we can't get around it. We have to use optics. So currently, we are addressing these qubits optically using free space optics, right? Lasers across the spectrum of visible and IR. These lasers come in from free space. So these are shone in from apertures in the vacuum chamber where the trapped ion sits. And this works really, really well. We're able to obtain extremely high fidelities, as I mentioned, and we're able to scale up to that 100 or even multi-100 qubit level in this architecture. Of course, this can be tiled as well. But this does start to have limitations when you start thinking about, well, what's orders and orders of magnitude? Maybe not 100 or 1,000 qubits, but how do we really get this thing to 1,000,000 qubits, right? Where now the word utility scale quantum computing is all the rage, right? If we're looking at DARPA as the benchmark, and we were just admitted into stage B of the DARPA QBI program. So obviously this utility scale is very top of mind for us. And to get to that, level of number of qubits that are going to be required to access the most high value, maybe not to access utility at all, but to access the most high value applications that have the most utility, we will need to scale. And at that point, there are pretty strong arguments that this free space beam delivery is simply not going to work for cost, for form factor, and really just fundamental space constraints. How do you get that many beams independently controlled into such a small region where these ions are actually operating? So to put a little sort of cartoon image in your mind of what that actually looks like, on the left is what a nicely stylized but photograph of a beam delivery looks like in a current trapped ion quantum computer. I think this is common across AMO and across trapped ion or other matter-based approaches. You got a lot of free space beams. You're sitting generally, a lot of the beam handling is done on an optical table with conventional optomechanical mounts. As I mentioned, there's real scaling challenges around the trap size being very small, needing to address these things individually at scale. So we need to go to some kind of architecture that allows us to deliver that light into what we call the physics package, into the chamber where the trapped ions are located on fiber, first of all. So we don't want to be shining things over free space apertures. And then we need to be able to further launch those beams from near or within the same chips that work in the trap into the actual ions, which are sitting trapped, of course, just above the chip. So we need to deliver by fiber, and we need to somehow get that light in a very micro fabricated way, right, in a way that's very integrated in order to individually address these ions. And there's various different wavelengths at play. I think Jeremy did a good job of talking about that. Challenging wavelengths to work at traditionally. If you come from the telecom or IR background, right, things work really, really well. Fibers work really, really well. You're at a good spot for microfabrication around critical dimensions and so on. None of that is impossible and visible, but it does become much more challenging, right? You get that omega to the 4 dependence of optical scattering. That makes everything harder, right? You're going to have much more of a challenge dealing with scattering losses. Alignments become more challenging. Critical dimensions for things like gratings. Here in the cartoon, we've pictorially represented gratings being the sort of mechanism to get light out of the chip and into that just few micron standoff where the ions are levitating. The critical dimension needed in order to get a really, really good and precise grating can start to stretch the limits of what typical foundries might offer in their photonic stack. So we've had to put a lot of innovation into that as well. Just a really brief snapshot of some of the projects that I'm able to talk about publicly. Of course, this is not a representative example of everything going on in photonics, but what we've poked our head above water to talk about. Large variety of test beds and capabilities in the lab. We do integrated photonic testing at room temperature, but we also do integrated photonic component testing on actual trapped ion chips that are fully integrated into our trapped ion quantum computing test beds. So we have dedicated integrated photonic test beds that are meant to take trapped chips that have photonic components integrated in them in a vacuum at the temperatures that they will be operated at, with beam delivery, really in a representative environment. Of course, you can do a lot at room temperature, a lot at atmospheric pressure, but you do want to do that full functional trapped ion testing. So we do that as well. Some of the work we're doing is not so sensitive to that. So it is outside the physics package, outside the chamber. It is at room temperature. Still going to need a lot of lasers, still need to process those beams, still need to modulate them. So, shrinking that, getting that a little bit more efficient, with a better form factor, a little bit cheaper. We do work on active control with modulators. But really what's more challenging here is that trap integration that's going on well inside the physics package, and a number of different opportunities working on. We talk about this collaboration publicly with Sandia National Labs for, they're of course incumbent experts in this area and have done a lot. And of course, we're going much further as well in our own integrated development. Usual components you might look at, probably nothing shocking here, right? You need to, you have efficient fiber chip coupling. The packaging problem chases me wherever I go. There's no panacea for it, telecom or visible. Again, it becomes more challenging and visible because of those tight tolerances. To the previous question that was asked, I think, yeah, by the gentleman from Microline, I think the CTE matching at when you go down to cryo is a challenge. I think that's something that does need to be worked on. It's can be addressed carefully, but because you don't have access to these epoxies, you're going to have packaging solutions that involve a more creative way of fixing fibers to chips, and that's going to have to be studied. And we do study its robustness to the large temperature swings when you take a sample down. We work on a lot of platform development. So we are working on our own customized photonic integration or integrated platforms for waveguiding silicon nitride, an obvious material that we're very interested in and use a lot. And that does co-integrate with the other trap functions. And then, of course, along with all that, you have the two more typical passive components. I would say really the most challenging and perhaps the one where the most interesting new stuff is going on is really around how you distribute that light. How do you launch that light? How do you first get it from a compact bundle of fibers that's coming into the chamber? And then how do you distribute that light to a trap chip or a number of trap chips? And then within those trap chips, how do you launch that in an appropriate way that preserves everything and is able to respect the sometimes quite challenging power budgets? And that's another aspect we run into, and I think the whole industry is running into, where first of all, you're working at visible, where damage thresholds can be punishing. Second of all, you do need to preserve a lot of that power. And while loss might not be a critical impact on the quantum information like it is in photonic quantum computing, there's a realistic limit to how much power a single fiber can take, or a single junction between a fiber and a chip can take. And can you preserve that amount of power that you need to ultimately launch at the ion when you have these cascaded losses? So working a lot on that. Just to name a few other components and sort of open challenges where others may be able to help. Stray light mitigation is a big one that interplays both in the trap development, the photonic integration, but also anywhere you have any kind of junction or any kind of component that's near the ions. You have to worry about where the light is going to minimize crosstalk. I mentioned ultra low loss problem, which is, I think, been a ton of progress in the last few years in the telecom fabrication techniques. Probably not as much in the visible, so that's something we need to drive. And then, of course, being able to do this repeatably in a tiled way. To allow that scaling is, no longer a science experiment and really becomes a real manufacturing challenge. And that's something we're paying close attention to. So I think I was told 6 minutes, so I'll leave it there. I think I'm right at time. Happy to take any questions.
Great, thank you so much, Zachary, and congratulations on now what you're achieving at Continuum. So what are the critical dimensions you were discussing? What's the smallest dimension you need for these apodized grating couplers?
Yeah, I wouldn't have that number offhand. I'm not sure I could share it if I did, but it does stretch. I will say that it does stretch what the typical, not what the semiconductor industry can do, but what's typically applied in most foundries for being able to etch a silicon nitride waveguide.
Sure. We have a question in the chat from Evgeny Pustovalov. Evgeny, would you like to unmute and ask your question?
Yeah, Evgeny from Corning. I have a question. What is your definition of logical qubits? You mentioned that you have 50 logical qubits. You are able to perform fault-tolerant operations with them?
So a little outside my wheelhouse, right? I'm not a error correction fault tolerance, but really what that means is you've encoded a qubit using multiple qubits in a way that improves your performance. So you've redundantly encoded quantum information in a way that allows you to do gates between multiple encoded qubits, and in a way that improves what the fidelities of at least some operations would be if you were using the individual qubit. So I think sticking close to the very traditional and conservative interpretation of what a logical qubit is.
Yeah, but I'm just curious. So you mentioned that you have 98 qubits and 50 logical, and it's strange that you call them logical, but anyway, okay.
Well, just a reminder, so logical, which means encoded, right? So the ratio of logical to physical, right, could be 10,000, could be 1,000, could be 1 or 2, right? It just means you've encoded and you've improved. Of course, you'll need to increase that code distance and increase that overhead in order to drive error rates lower. But the conventional, logical qubit is 1,000 to 1. That's when people are talking about logical qubits where the error rate has been suppressed to, 15 nines or something like that. So obviously the industry is not there yet, but we're all getting there.
Charles Goller from Icon Photonics, what's on your mind?
Thanks. Nice to see so many places that we saw in Bristol in strengths that
Sorry, Charles, I am not able to hear your question. I think your mic might be muffled, or maybe it's just me. Are others able to hear him? Yeah, something up with your, I think up with your mic.
It does sound a little muffled. Charles wrote in the chat, what about the targeted losses and power handling? I guess you mentioned power being really important.
Now, is it better?
Yes.
Oh, okay. But yeah, John, you were saying, so you mentioned also power handling, I think at 532 nanometers. What did you already achieve in terms of coupling efficiency? What would be your targets, and do you have an idea about this power limit, power handling that you would like to have?
Sure. Yeah, a little limited what I can say publicly. I can, maybe discuss a little bit more offline in a one-on-one. I can say that we've achieved fiber chip coupling, which is for visible pretty state of the art, considering the constraints that we're facing, right? In the types of couplers we're able to use, the types of layer stacks we're able to use, but it does need to improve. As for the ultimate target, it's not like, again, if some of the numbers thrown out there in photonic quantum computing where you're talking about milli-dB of coupling, not even close to that. So we have luckily a lot more power budget, a lot more loss budget. But yeah, I think certainly sub-dB regime, even sub half dB regime is where, for some of the interfaces, for some of the wavelengths, not all of them, we will need to be for fiber chip coupling.
Okay.
Josh Nunn, Orca Computing, what's on your mind?
Hi, Zach. Good to see you again. I just thought I'd just ask you directly to remind me if it's public. What's the species you guys are using? And then you mentioned 532. Do you have a little list of sort of wavelengths that you need to be able to manage?
532, 493, and there's others. I'll that's my own newness, my novelty to the trap.
Okay.
Going. So there's a long list, but yeah, I think that the typical ones that you mentioned and that are familiar. As for the qubit species, there's a couple other ones and a couple always in discussion. So I'll also abstain on that one. And also, yeah, good to see you, Josh. Long time.
No worries. Okay, cool. Thanks.
Right, Zachary, I'd just like to quickly touch on, you've seen two very different quantum roadmaps now, with Xanadu and now Continuum. What photonics capability do you think the entire industry is collectively underestimating? And, what are the common challenges?
Sure, I would again come back to packaging, but beyond not just the mechanical aspect of packaging, but the design aspect too, right? Which goes into the process flow needed to define and create very, very good couplers, whether they're edge couplers or grating couplers. This is an industry-wide problem. It goes outside even quantum. If you talk to companies that are working on datacom transceivers, if you press them long enough, they will say, yeah, actually, if we could get this much lower transmission loss, this much improved transmission loss in our fiber chip couplers, then it opens up realms of possibilities, like being able to completely overhaul the architecture to eliminate some of the digital processing that could make much cheaper, much more power efficient transceivers. So across the entire integrated photonic industry, I again come back to packaging as that holy grail, which I wouldn't say is underestimated. Most people do admit this or talk about this, but compared to how much has been invested in other problems which are either less important or less risky or already solved, packaging is certainly an underserviced area.
Zachary, thank you so much for joining us. It was great to have Steve Sanders in Bristol last week as well. So thanks very much from Continuum.
Thanks for having us.
At this stage, I'd like to bring in Steen Kuivers from Ligentech. We've discussed silicon nitride, and Ligentech are one of the leading suppliers of ultra-low loss silicon nitride photonic integrated circuits. So Steen, please tell us more about what you can do for these companies.
Thank you very much for the introduction, John, and nice to see you all here today. So for those of you who are not familiar with Ligentech, Ligentech is a process design house and a PIC manufacturer for silicon nitride-based PICs. We have our headquarters today in Lausanne in Switzerland, but we also have offices in Belgium and France. And we support many different applications, but also many quantum customers, quantum computing customers. And we do that with a number of established silicon nitride platforms that we have built over the past decade. So we have a few different flavors targeting different wavelength ranges. And each of these established platforms is extended by a number of so-called process modules, which we use to bring other functionalities to the platform. This can also be used, for example, to build more complex multi-layer silicon nitride stacks. And all of this is also, in terms of design and layout, facilitated by our PDK, which is supported by the major software players in the field. To give you maybe a quick example of what we can achieve on our passive silicon nitride platform, we achieve on our 350 nanometer thick silicon nitride around 4 dB per meter propagation loss in a strict single mode waveguide, and below 0.5 dB per meter in a wider 3.5 micron waveguide with good within wafer and wafer to wafer variability. And so this is something that we can also use, for example, to build low loss delay lines with propagation losses going close to 0.5 dB per meter while retaining single mode operation, and also while retaining a relatively compact footprint owing to the still quite thick silicon nitride. Now at LightGenTech, we also put a lot of effort on extending the silicon nitride with active components, such as detectors, but also with electro-optic modulators. So here you can see an image of a chip that we made with electro-optic lithium niobate modulators on our silicon nitride for ONC band in this case. Maybe important to highlight is also that our PICs are manufactured in a 200 millimeter automotive fab. So we also have a strategic partnership together with XFAB and Accelerprint to manufacture these PICs, both at lower volumes, but also at higher volumes, as well as the heterogeneous integration. So I'm happy to, you can always reach out to us if you want to learn more about our platforms and heterogeneous integration offerings. And I'm happy to take any questions.
Great, thank you so much, Steen. How do you currently work with quantum hardware teams? How do you typically design with them on your PIC platform? And are you seeing standardization kind of emerging between the companies?
I would say right now the landscape is quite scattered. So generally we engage in a general roadmap discussion where we develop the separate components like the lithium niobate modulators or passives and so on, and then we gradually bring all those components together on a single PIC or a few PICs. Right now, as you saw also in the previous presentations, depending on the implementation, many different wavelengths are being used, so they are a bit scattered in that sense. But of course, maybe within the same wavelength ranges, there are a lot of similarities that where we can bundle forces.
Sure. And is your silicon nitride able to fulfill the power requirements that they were discussing in the previous talk? Yeah, basically.
Yeah. So in terms of power handling, I would say yes. It depends a bit on how far we need to go, but silicon nitride is well suited to handle high powers. And in terms of propagation losses, especially if we go then to the visible range, we also have a lot of opportunities there with our thinner nitride platforms, for example, the AN150 platform that I showed. So yeah, if you're interested in specific wavelengths and specific loss numbers, I'm happy to discuss in a one-on-one.
Brilliant. Well, you've heard it from Steen. Please contact them and pick it. So thanks so much, Steen.
Thank you.
So I'd like to bring in now Cesare Alfieri from Femtoprint, who uses femtosecond laser 3D microfabrication to create custom micro-optical structures directly inside glass. So for the ion trapping community, this can be hugely valuable, as we learned in discussions in the Quantum Industry Summit in Bristol last week. Cesare, please tell us more.
Thank you very much. Good morning and good afternoon to everyone. So I want to quickly introduce you to Femtoprint. We're a Swiss company. We are sort of a glass glass foundry. We are a contract and development manufacturer. And we are hiring now more than 40 people. We're active in many domains, but today I want to talk about quantum. So we work on glass, as I said. Our main quantum focus is on glass ion traps. So glass has some benefits. First of all, it can be precisely machined with our technique, but it has also very high breakdown threshold and excellent dielectric properties. and for the trap community in particular, low loss tangent. We can work with different glass types, also to have a city matches with the surroundings. So what is our value proposition? We can start from the very beginning of a project. We're not afraid about low quantities, but we can also scale up. So taking the customer with us in a joint development up to production. So here volume is a bit shaded because at the moment we haven't seen a volume production in quantum yet. So what can we bring? We can have optimized trench design that we can develop with our customer for a good and safe electrode installations. We can have very complex 3D structures. We can have multi-layer traps that can be laser welded together with our technology. And we can also offer metal deposition with sputtering or evaporator. But today I want to tell you a bit more also about our photonic connectivity platform. So we work a lot with optics and photonics customers. In there, we work producing fiber alignment features, so V-grooves, Hall arrays, fiber ferrules. We can also inscribe waveguides in glass, and we can shape the glass in 3D in order to have mirrors, lenses, and in general, miniaturized micro-optics. And this happens with a single micron precision. So now imagine if we can monolithically integrate all these features in one device. So I'm talking about traps with maybe already precise fiber inlets, with a waveguide and with refractive optics. I have to say that especially for waveguide, we developed the platform for telecom wavelength. So everything that was said before, especially by Quantinuum, applies also to us. So there is a challenge, but we would be very happy to take it. And with this, I'm open for questions. Thank you very much.
Great, thank you so much, Cesare. What volume can you manufacture these complex 3D structures?
So when we're talking about traps, at the moment, I would say we have not received requests for more than tens of traps. But this is far from our capacity limit. When we're talking about micro-optics, so devices that combine lenses, waveguides, and ferrules, we are now ramping up with very important telecom customers. So we are now in the tens of thousands.
Right. Okay. So from what you've seen from IonQ and Continuum, would it require a big redesign of their traps to use your glass delivery systems, would you say?
I guess yes. I don't know how happy they would be to redesign a trap architecture, but I think we can be a very interesting way to explore in parallel with what they already have, to maybe produce a next generation trap with more complex features, both on the trap side because of the 3D and on the optical connectivity.
Fantastic. Well, I hope you take that offline with them and discuss it further. So thank you so much for joining me, Cesare. So our next speaker is Poulad Imani, CEO of Icarus Quantum, a company tackling one of the hardest problems in the field, so creating practical room temperature quantum interconnects. So please tell us more, Poulad. The floor and the attention of everyone is yours.
Thank you so much, John. It's a pleasure to be here, really. It's nice to see so many familiar faces. My name is Poulad. I'm the CEO of Icarus Quantum. We are based in Boulder, Colorado. We spun out from NIST, from the Quantum Nanophotonics Group, and we make quantum interconnects for a variety of different qubit modalities, which I'll tell you more about in a bit, if I can advance. There we go. So our motto is that after a certain point, if you are scaling quantum computers that are specifically working at cryogenic temperatures, then for practical reasons, it's nice to be able to modularize them. And that point can be thousands of qubits, can be tens of thousands of qubits, depending on the modality that you're using. We specifically we're focusing on superconducting qubits, which work at millikelvin temperatures. And so the requirements are much more stringent when you really try to scale. Even when you're looking at how many coax cables that are going down to that millikelvin plate in a quantum computer, it is it gets crazy, like even after the few hundred qubits. So what we're trying to address is, let's make these devices modular, but let's not make the whole delusion fridge the size of a football field. Let's have the links between these modules to be room temperature. So that's where we come in, photonic quantum interconnects. And we're doing this with a variety of kind of product portfolio. So we're starting with single photon sources, and we're trying to be very efficient, very robust, very scalable in everything that we do. So that's where we already have prototypes, which I'll talk about later. And the next step is to build entangled photon sources that are on demand, that are efficient. And the last step is to convert the entanglement from the photonics domain all the way to the superconducting or spin domain. And so for that, you need microwave to optical transducers. Yeah, so we're working on all of these together, and there are similarities between all of these products. And the way that we do think about the interconnects is a little bit different than the usual microwave to optical transduction that people in the superconducting world think about. We're starting in the photonics world and then moving to superconducting qubits. And let's see if I can play this. There we go. So we have our entangled photon source that generates entangled photons, routes them through optical fiber, and then you go to transducers that entangle a bunch of superconducting quantum computers. And here are the applications, and that's it. So easy peasy. And again, the idea is our devices don't work at room temperature, but the links are. The links are fiber optics. Photons are the only things only medium that can transfer quantum information at room temperature. So let's stick to that. And how are we doing this? We're using semiconductor quantum dots. So this is not new. Our NIST group has been working on this for a good 30 years. There are many other groups that, especially in Europe and China, that are doing fantastic work and like really pushing the boundaries. I have 3 great companies, Quandela, AGIC, and Sparrow Quantum, who are really at the forefront of working with these quantum dots. And so why quantum dots? And for one of the reasons is, well, you can actually fabricate these at scale. However, you have to grow them in very pristine conditions. So for that, we're using molecular beam epitaxy. But once you start embedding them in optical cavities and electrical structures, then you can use them as artificial atoms, as 2-level, 4-level systems. And depending on how you excite them, you can get on-demand photon sources. And this can be both single and entangled photons. And these are really huge structures compared to atoms. These have 1,000, 10,000 atoms in them. And somewhat as a result of that, they are very fast. So you can use these at gigahertz rates. There we go. Okay, so I mentioned that we have single photon source prototypes. So this is one of the chips that we fabricated. So here's a schematic of our device. We have a quantum dot embedded in this kind of vertical plano-concave cavity that's kind of monolithically fabricated on the chip. And then we excite the quantum dots from the side. The quantum dot emits in the cavity mode, and then we collect that into fiber directly without any need for pump rejection or anything like that. And so far, we've seen end-to-end single photon efficiencies of 40% with evidence of 60%. That is, pulse goes in, what's the probability of a single photon coming out in the fiber? And we've seen acceptable G2 numbers. So this is kind of looking at the photon purity of about 99%. We're edging towards 99%. And another way of kind of quantifying how good our system is the Purcell factor of the cavity. And we've gotten up to 5, and we're ideally want to be somewhere between 10 to 15. So we're actively working on that. Now, on the transduction side, again, everything, our bread and butter are semiconductor quantum dots. So even our transducers have quantum dots in them. So this is how we've been doing it at NIST, and we are changing the architecture, but this is the thing that we can publicly talk about, that we have a quantum dot at the center of the system, and we have surface acoustic waves that mediate the interactions between microwaves and optics on top of the quantum dot. And with this type of system, so this is one of the fabricated chips that we have that have surface acoustic wave kind of resonators around the quantum dot and interdigitated transducers, which basically shake the surface of the system due to the piezoelectricity of the substrate that we have. And they basically generate phonons out of microwave photons that would then go modulate the light that's scattered from the quantum dot. So taking a microwave photon, turning it into an optical photon. With this system, we've seen very low efficiencies of 10 to the minus 10. This was 3 years ago, but since then we've made many orders of magnitude improvements on many fronts, but we haven't put all of these together. So for example, in this system, we didn't have any type of optical cavity that I just showed you for a single photon source. So our collection efficiency was at 0.1%, and right now we're up to about 50% there. So that's one of the improvements that we did. So what can we do for you? What can you do for us? We are a quantum interconnect company. We make good photon sources, good transducers. We do not make quantum computers ourselves. So we're actively looking to partner with specifically photonic and superconducting quantum computers. And yeah, I have some of the logos here. So some of you are already on this call. So if you can see this, please reach out. I would love to talk to you. Thank you so much.
Great. Thank you so much, Prahlad. And what is it that you need from the photonics industry? Is it from foundries, packaging houses, platforms to scale your technology even further?
Yeah, so many things. One thing that we're actively working on with some of our partners is fiber to chip coupling. And as you saw in our architecture, we need both edge coupling and surface coupling. So edge coupling is not that big a problem for us. It's more like the problems that Zachary was talking about, because it's just the pump. It's not, we don't need that to be on it, at milli-dB levels. But on the surface coupling, in the surface coupling regime, we have to really work at 95, 96% efficiency. So that's very challenging, and that is something that we're again actively working on, not by ourselves but with our partners. And everything has to be cryogenic, so our quantum dots work at 4K. The transducers will work at millikelvin, so everything has to work all the way down to millikelvin. But nevertheless, 4K is the first step.
Well, as Josh says in the chat, this is very cool. So yeah, congratulations on what you're achieving. Everybody should contact you and work with you. So thanks for joining us. And our next speaker is Sean Sullivan, CTO and co-founder of MemQ, one of the leading companies developing practical quantum memories for scalable quantum networks and modular quantum computing. Sean, the floor and the attention of everyone is yours. Thank you.
Great, thanks, John. Great to be here, and good morning, good afternoon, everyone. I'm Sean Sullivan, one of the co-founders of MemQ. We're a startup company based in Chicago. We came out of the University of Chicago and Argonne National Lab, and our focus is really on building hardware and software for connecting quantum systems together. So as has been evidenced in some of the previous speakers, building a monolithic quantum computing system is a very challenging problem. There are a lot of key bottlenecks, key challenges to overcome in terms of manufacturing repeatable qubits, complex control systems, for addressing individual qubits in terms of lasers, et cetera, limited cryogenic space, and as well as, depending on the architecture, limited intra-QPU connectivity. So we see sort of this evolution towards interconnected modular quantum computing as a very clear path forward, as Prahlad was also just talking about. But there are several key challenges there. MemQ is working to address some of these challenges. So when we think about these modular quantum interconnects, their competitor really isn't other types of interconnects. It's actually things like circuit knitting. So if we imagine breaking up a quantum problem, a circuit into smaller chunks, and then trying to stitch that back together using classical processing. Of course, there are some limitations here. So we looked at this circuit knitting versus a purely quantum channel interconnect to really be instructional for the types of quantum hardware, interconnect hardware that we need to develop to make this feasible. So we broke this down into a very simple multi-qubit circuit. This is a multi-qubit GHZ state generation where we compare making multiple cuts in the circuit knitting approach versus actually having interconnects. So in the case of the circuit cutting approach, as you increase the number of cuts, there is an exponential scaling in the overhead with the classical processing. So eventually you hit a very clear limitation in terms of how big of a circuit you can reconstruct. And what we find is that for a quantum transducer, an interconnect between a qubit and an optical link, there is a clear trade-off, a point where if we reduce the added noise by roughly a factor of 10 from where we are today, then we can really see this clear benefit over the circuit knitting approach. Now, as we think about building these distributed quantum systems, both in terms of pure quantum channels, as well as in these circuit knitting approaches, we see it evolving similar to how the classical compute environment evolved. So going from small scales, nodal to cluster to campus, sort of data center-like scales, and ultimately to WAN and long distance as the needs and technology evolve. So MEMQ is developing an extensible quantum network architecture that can address the quantum connectivity at all of these length scales. So we're building hardware, quantum network interface controllers that interface closely with different qubit modalities for interfacing with matter qubits extracting photons. We're building quantum memory modules for helping to synchronize photon-mediated entanglement operations in a network. And we're building quantum control chips. These are integrated photonic nonlinear chips for delivering pulses of light exactly where and when they're needed. So I'll go through just a few of the things we've delivered on each of these areas. So in the quantum network interface, we've developed chip scale interfaces for solid state qubit systems on commercial 300 millimeter wafers. We've made these very small mode volume, high quality factor cavities for interfacing with single rare earth ions very repeatably. And we've been working recently with customers to develop integrated photonic solutions for atomic qubit systems as well. These drop into existing free space optics and basically provide an interface between arrays of things like neutral atoms with fiber arrays on the PIC. And these include active photonics for bidirectional operation. The control system, some of our customers have need integrated photonics or photonic solutions that operate at low temperatures, so a variety of temperatures. So we've developed ultra small footprint optical resonators based on commercial Tiflin that work at cryogenic temperatures all the way up to room temperature. And some of these designs, these very small footprint modulators, also have very low insertion loss, less than 0.1 dB. And lastly, as our name implies, we've been developing quantum memories for helping to synchronize these operations, coherent optical memories for photon storage. These again are based on commercial silicon nitride PICs, where we do backend integration of our own erbium-based, erbium-doped thin films. We've done ensemble-based coherent storage with optical coherence times in excess of 64 microseconds and spin lifetimes in excess of a second on these fiber packaged chips that are ready to plug and play and we've delivered a few of these to customers. So that's MEMQ. Would love to discuss your quantum connectivity needs. Please feel free to say hello or ask any questions. Thanks.
Thank you so much, Sean, for joining us. So if the photonics industry could give you one breakthrough in the next 2 years, materials, integration, packaging, what would accelerate MEMQ's roadmap the most?
So there are two things. I'd say that, as not to belabor the point, but the packaging is a huge focus. So we've spent a lot of time developing cryogenic packaging for the photonics. So we've explored a variety of epoxies, CTE matched substrates, as well as photonic wire bonds. These operate in the telecom fairly well, but as we develop solutions for customers in the visible, that again is a huge challenge. And then secondly, a nonlinear photonic material that is easily scalable, that doesn't have some of the limitations in terms of things like photorefractive effect at visible wavelengths for power handling. I think that would be another huge benefit.
And just something that links back to what Continuum was saying, Zachary was saying, is you must be getting close to the critical dimensions you're able to achieve scalably with your 1D photonic crystal cavities. Can you just comment on that?
Yeah, so absolutely. We had to work very closely with the foundry on some of their newer processes that were only available on dedicated runs to get to these critical dimensions. Part of this was done in partnership with some DoD agencies, so we had some help there. But this is absolutely a problem, and this becomes exacerbated at the visible wavelengths, as Zachary was saying. There are a lot of these foundries that are offering, kind of advances in terms of the smaller critical dimensions, which I think is absolutely needed.
Thanks, Sean. Well, Josh has commented that this is also very cool, so I think you should speak off Josh at Orca Computing. So thank you so much for joining us.
Thanks,
our next speaker is, we've heard packaging mentioned a lot today, so we're delighted to welcome Stefan Heinemann, Managing Director and VP of Sales at Fix Photonics Assembly, one of the industry's leading specialists in packaging and assembling photonic integrated circuits. Stefan, please share your slide. The attention of everyone is yours. Thank you.
Thank you. Thank you so much. I hope you can see my screen.
Yes. Yeah.
So I got 2 minutes to introduce Fix to you. We are a pure play packaging foundry. Our headquarters is in Enschede, the Netherlands, and we have opened our US facility early 2024 in Bozeman, Montana. We're happy to be here. Thanks, John and Helena, for having me here and represent what we do in photonics and packaging. So our perfect working point is, as you can see it on this slide, is just before the OEM customer gets his parts. So we like to get involved as soon as possible to consider packaging, and even in the design phase, or even better in the idea. But when you start taping out your chip, that's when you should also consider packaging to make this as painless process as possible. And then we work with you through the individual phases is shown all the way through early product and then scaling. Our expertise is in photonic interconnects. That's our core expertise, and great that this was mentioned a couple times before. And I just put down a few samples, show a few samples here. I mean, obviously we do the conventional stuff, edge coupling and gradient coupling. We also have spot size converters, but really the main focus is on how we can reduce the coupling losses and how can we make this scalable. And one technology that we found very much of interest, especially in the prototyping phase before you scale it, is printing of optics. The reason why, because it gives you a lot of tools to quickly validate your optical designs. and also go. So I show over here in the printed optics on fiber, where we print lenses, periscopes, beam deflectors, and even nanostructures at the tip of fibers. But you can also go 2D, and I saw that caught especially my interest when Quantinuum was talking. Zach was talking on behalf of two-dimensional arrays that you need for their application. And this is, we do a lot of work in the optical communication and the co-packaged optics space. So we're very well acquainted with low pitch, high coupling efficiency, all kinds of different geometries. And that, those two pictures in the center give you a good summary of what we do in terms of make the coupling losses less than 0.7, less than 0.5 dB, make it in a small pitch, and make it also dispersion free. So you can use this for a variety of different wavelengths. And then on the lower left, you see, micro optical benches, where we, couple different media together, route optical signals. Optical isolators are obviously a very important part of this. And this is, miniaturizing the whole optical benches and making it compatible to a wide range of operating temperatures. And obviously, we have to have scaling in mind. So we do this not only manually, and after we've done the initial design, we switch this over to production and fully automated assembly. Just to give you one of our working points is highly integrated laser, or what I call it, good photons, if you want to say so. And this is just one example of one of our customers that is in the public domain. But the idea here is sub-hertz Lorentzian line width lasers that are widely tunable. I also want to point out 100 nanometer plus, which is an important feature for our customers in the quantum space. And that's at a variety of wavelengths. Right now, we're going down from the visible all the way to the near AR, and tens of milliwatts of output power. Now, next step that we see coming is how do we scale this and make this redundant? And one of the trace that we're going is after coherent beam combining on the chip or multiple optical networks. Let me bring up one more slide if it does come. Yeah, so what we see in quantum, just to summarize that, our customers are in atomic clocks. Everybody mentioned packaging is one of the bottlenecks. Very happy to hear this. We are here to help you as much as we can. So atomic clocks and frequency combs are what we see really coming very close to industrialization, where we go from tens of units to hundreds and even more. Very narrow line with lasers, as I showed before. And then I just want to point out, as I heard this, optical interconnects is, again, our core expertise. 400 nanometers, we have recently demonstrated 400 nanometer wavelength in cryogenic temperatures. I also made the comment that, yeah, we live in Montana, we know what it is, but Montana, as you may know, is a hotbed for companies like on cryostats. So we have a very good ecosystem in optical interconnects at very low temperatures. And with that, I guess my 2 minutes are up, and this is just the outlook of, I think, what everybody has in mind. And I'm probably preaching to the choir here, but I always find this a very interesting picture, how you can bring this kind of complicated optical setup on the left onto the PIC, and that's what we see as the future. Thank you so much.
Stefan, thank you so much. It's great to see Fix already working with the entire ecosystem and solving everybody's packaging challenges. So if anybody has any fresh challenges for Stefan, please do get in touch. In the interest of time, Stefan, we're going to move to the next speaker, which is Josh Nunn, Chief Science Officer at Orca Computing, a company at the forefront of photonic quantum computing, and one of the only vendors already delivering deployable quantum systems into real data centers. Josh, the floor and the attention of everyone is yours.
Hi there. Thank you. Yeah, thanks so much. Thanks for the invitation. It's great to have a chance to speak to everybody. And yeah, without further ado, I'll just go on and tell you a bit about what we do. If you're able to see these slides. It's amazing to be in the company of Quantinuum and IonQ. We are a slightly smaller outfit than those guys, but we are a full stack quantum computing company. And in particular, something that differentiates us that yeah, you just mentioned, John, is that we have products that we're producing now, and obviously our ambition is to move towards more powerful and ultimately error corrected machines. So we came academically from Ian Walmsley's group in Oxford, around 40 of us, and our headquarters in London, in Paddington. Please come to visit. And we have an integrated photonics team out in Austin. So our roadmap includes there was a previous product last year. Currently, we're on our PT2 system that you can buy for around $1.5 million if you fancy one. And next year, we're looking at a quantum advantage system. And then, the last thing I wanted to point out on this slide is around the end of the decade is when we would like to be able to start producing error-corrected systems. So just a brief comment on these current products, the PT systems. We've deployed 10 of them so far. Which is actually just because quantum computing is very early, that's actually quite a large fraction of the deployed systems globally. It's around a third. How does this system work? It's a boson sampling system. And the reason that's useful for machine learning is that what a generative AI system does is it takes a sample from what's called a latent distribution, and it deterministically converts it with a neural network into an output data distribution. And what's interesting is that with a boson sampler, you can access latent distributions that are not accessible with a classical machine. And that means that your push forward distribution, your data distribution, covers output data that are not easy to access with a classical system. So that's led to some quite interesting benchmarking results that we found. I won't explain this diagram except that the boson sampler is closer to the target in this picture. It's just a way of visualizing how that performance improvement can manifest. We've been able to show improvements in generative chemistry. And if you look at how the systems train, what you see is that so the blue line is the quantum system, and you see that so the y-axis here is the accuracy. So lower is better, and you see that it trains faster. So it achieves a better accuracy, but it also takes less time, and therefore there's a power consumption saving there, which is quite that's really what's got us quite excited about these early stage systems. A couple of other things you can do with these systems: you can solve binary optimization problems, kind of Ising type problems, similar to what you would do with maybe a D-wave system. You can apply these types of systems to things like time series analysis, fraud detection, and we were quite pleased that we've been able to really make a hybrid system working with NVIDIA and also the team in the Poznan Supercomputing Center to make sure that the whole system is integrated with a GPU cluster. So how do we build these systems? We use squeezed photon sources with extremely high efficiency, around 90% efficiency, and these systems have around this PT2 system is around 90 Q modes. So in terms of yeah, the number of sort of computational elements in the distribution, and some of the things we had to engineer to make that work was a very stable fiber type processor. And we also have work on integrated photonics to move towards a very fast low loss switching, which is something that a lot of teams are working on as well. So here, this really overlaps with the stuff that we saw from LiganTech, is looking at lithium niobate on a silicon nitride platform. And also one of the things that is very important to us, because we're in the photonics game, is looking at ultra low loss edge couplers, chip fiber edge couplers. This is a multi-layer stack that gives you a good match to a fiber mode. And so, moving in this direction is an important challenge for us, as it is for a lot of the teams on the call. This is the modulator system that we're developing. Part of the way this system works requires interlayer transitions. So this is sort of multi-layer silicon nitride that we need to eventually move towards doing cheaply and efficiently, which I have to say at the moment it's not that cheap and not that efficient. This is about wafer bonding. The last thing I'll mention is that some of the heritage of Orca is around atom light interactions. And so one thing that we're quite excited about is starting to move beyond the regime of just linear optics and starting to implement something that looks like a gate between photons. And to do that, we use this protocol of off-resonant cascaded absorption. So that's where the name of the company comes from. It's an acronym. My phone is telling me I need to shut up. So I will just briefly wrap up by explaining. Oh, well, okay. So the way to make this interaction really strong is by using a microcavity. So we're interested in scalable arrays of microcavities. That's an interesting area for us. Once you have this type of nonlinearity, you can start looking at not just the single layer neural networks, which is one way of thinking about the PT system I described, but multi-layer quantum neural networks, which is then you start having a much more powerful machine learning system. And the final thing you can do, which is really exciting, is that when you have these nonlinearities, you can build fault-tolerant quantum computing systems with much higher loss tolerance and much smaller footprint than linear architectures. So with that, I'll just wrap up with a list of asks. Yes, we're looking for foundry transfer, multi-layer silicon nitride and thin film lithium niobate. I mentioned cavity arrays. Every single person has mentioned packaging. That's super important and very interesting for us. And of course, if anyone is interested in the machine learning stuff I touched on, we're quite interested in thinking about more use cases with potential end users. So yeah, with that, I'll finish. Thanks.
Great. Thank you so much, Josh. Amin Abbasi from IMEC, what's on your mind?
Thanks, Josh. Interesting. You had a slide about the modulator lithium niobate. What was the loss? I think it was half a dB something. And what is the limiting factor to go down even more on the loss value?
Thanks. And I'm not the expert in the company on this, but I think the limiting factor on the loss there is that because the lithium niobate has a higher index. We need to, it kind of sucks the mode in, which is great for the modulation, but sort of at the end of that, we want to get it back into the buried mode. Yeah. And for that, we want to taper down the lithium niobate. And so those tapers, the losses are kind of limited by the precision with which we can engineer those tapers. And at the moment, we're running this fab out of UCSB. And so that tool has a limited resolution.
Okay, interesting. It will be great to touch on that one. We are doing similar things. Yeah.
Great. Thanks.
Dean Ivers from Ligentech, is multi-layer silicon nitride and TFLN something you can provide?
Yeah, definitely. I think we need to set up a call to discuss in more detail, because we're also, just like Amin mentioned, we're also doing similar things. So it would be good to learn where you stand today.
Great, fantastic. Yeah, thank you.
Fantastic. Well, thanks, Josh, again. So our final speaker today is Dylan Maguire from Ansys, a company whose simulation tools have become essential for designing quantum photonic systems, from the source all the way to the detector. Software that I've personally used for 14 years. So Dylan, please, the floor and the attention of everyone is yours.
Thanks very much, John. And yes, happy to join today. As Ansys, the world leader in engineering simulation software, now part of Synopsys. So bringing that simulation technology all the way from silicon to systems. I saw some fantastic presentations today on integrated photonics, and I think we've been a huge part of that and are very proud of that. And just to take a couple moments here to talk about how we can take that simulation from source to detector for quantum photonic integrated circuits. I think hopefully, as everyone's familiar with the numerical team, we've been involved in modeling integrated photonics in this space for a very long time. And we can extend that now to modeling those integrated photonic systems, including the quantum information in those systems now. So we have a technology stack that covers many different aspects of quantum information, including networking, looking at this from a circuit and system simulation perspective with our interconnect simulation tool. And this includes technologies like CVQKD. Sensing and clocks, we saw some good examples of photonic integration for reliability, for integration for packaging, and the core photonic simulation tools and the numerical products are key enablers of being able to design and optimize the components for those under a variety of conditions. Typically we would be associated with some of the data center applications, but of course these simulation technologies like GPU accelerated FDTD can be applied to materials and wavelengths across a wide range of applications. And finally, extending this into quantum computing, and now actually looking at the quantum information and the quantum state in the system and how that state is transformed by an integrated photonic circuit. So from things like gate level models, non-classical source modeling, and as well the overall design of experiment where you're actually tracking the quantum state and its transformation in that system. So just as a quick example of that, we look at non-classical source design with the Q interconnect. And one of the key questions in this type of application is, how does the source design overall affect the say the indistinguishability of the photons or the quality of the photons? There's a lot of aspects to this, things like the pump characterization and its delivery, so our laser source, how is that actually getting delivered to the resonant cavity, the resonator design itself, looking at the coupling, the dispersion in the model, nonlinearities in that system, and how the classical waveguide properties are actually imported into determining the quantum state. And we can use that classical information, classical simulation characterization of, say, the resonator here, and build a quantum model of the state, the biphoton wave function, with varying pulse input characteristics. And then we want to look at that as it's, that state is now injected into our system, is filtered, and is brought to, through maybe some processing to the detector and measured. And we can now look at that from a circuit level and see the transformation of that quantum state that we've now injected into the system as it goes through the filtering and it goes to the detectors and is measured. And then we can look at how the physical devices that we're using for that characterization or for that circuit itself, how maybe some non-idealities in those circuit components, for example, the couplers, could impact the overall performance of the design. So just a quick overview to connect not just the classical simulation of the photonic integrated circuit components, but now with the quantum state in that system and seeing how those two can live together. And so thank you.
Thanks so much, Dylan, for the overview. Can I just quickly ask how closely ANSYS is working with PIC foundries and quantum startups to create validated PDKs that reflect the real quantum performance of devices? So as part of the numerical team, we've worked for a very long time with foundry partners in terms of PDK enablement. This is primarily focused in the past on classical photonic integrated circuits, and we have strong foundry partnerships. I think we saw one mentioned one of the earlier presenters. In terms of extensions to the quantum space, it feels currently like the components themselves are quite new. There's a lot of custom component technology that goes into the core of these designs. A lot of that we can enable through relationships between foundries and the designers. But it does feel like at this point the overall PDK ecosystem for integrated photonics for quantum in particular is still maturing. Great. Well, thank you, Dylan. And thank you to all of today's speakers for sharing such valuable insights. The success and value of this meeting is really in the follow-up. So please do follow up with all the people. We're happy to provide intros to people who've spoken. So we're about to close this meeting for the YouTubers in the world and stop the recording. You're of course all free to go, but we're happy to keep the Zoom room open for a few minutes if there's anything you'd like to follow up on immediately. So can I ask my colleagues to please share and play the end and I believe the YouTube